Hi, I'm Adrian Shandro, and today I'm going to present a novel method for personal protective equipment recognition, which uses supervision signal from a pose estimator to train a spatial attention module. This is joined to work with Georgian Emilian Duță, Mariana Iuliana Georgescu, and Radu Tudor Ionescu from the University of Bucharest and Securify. Personal protective equipment are effective in hazardous working environments where people's life is threatened by dangerous chemicals, heavy machines, and so on. Even if their health is at risk, workers are inclined to ignore the importance of safety rules. However, having an automatic system that warns workers in real time at any deviation from the safety rules will be a great deterrent to imprudence. Another challenging aspect is scalability, since construction sites are usually large. Some of the very first systems developed for personal protective equipment detection are based on radio frequency identification. Workers have to carry some devices which are programmed to identify the equipment based on proximity. This method fails if the workers decide not to carry those sensors. Systems based on conventional machine learning methods, for example, support vector machines or decision trees, and handcrafted feature extraction exhibit poor modeling capacity. Such systems do not cope well under illumination changes, aspect variations, or occlusion. Researchers and engineers turn their attention to deep learning methods, which provide superior results due to their capacity to learn a hierarchy of features from large amounts of data. Our main problem with these methods is the lack of data variety. Such an example would be that there is a scarce data showing white sneakers on a muddy terrain. Our solution is to use an architecture which consists of three main components: a person detector, an articulated body pose estimator, and a classifier. The novelty consists in employing the pose estimator only at training time, providing pseudo-ground truth attention maps to improve the performance of the classifier. The pseudo-ground truth attention maps are shown in this figure on the left side, and they are used to train an attention mechanism integrated in the architecture of the network. In this way, the classifier learns to focus on personal protective items using knowledge from the pose estimator. During training, the input images are processed by three neural models. First, a person detector is employed. Then, a pose estimator takes the bounding boxes predicted by the person detector as input and generates a skeleton. Based on the generated skeleton, we can approximate the body parts of interest. From the current image, we want to teach the classifier if the person is wearing a helmet or not. Therefore, we give as input to the classifier the top region, a ground truth attention map indicating the head location, and the ground truth labels. The objective is to minimize the joint loss function between the attention loss and the classification loss. During inference, we apply the person detector on images, obtaining a set of bounding boxes. For each bounding box, we crop out subregions that can potentially contain certain personal protective equipment items and provide them to the corresponding classifier. Our method is fast and scalable on multiple streaming inputs. We employ the YOLO V3 object detector, which can sustain at least 30 FPS on modern GPUs. Pose estimation is expensive in terms of computational requirements, but it's used only in the training phase. Our personal protective equipment classifier is based on the MobileNet V2 architecture, which is equivalent with AlexNet in terms of accuracy, yet offers faster processing times. In this table, we show results of the MobileNet and MobileNet plus SAM baselines versus our MobileNet plus SuPEr-SAM on helmets, boots, and surgical mask datasets. On the helmet dataset, we outperform the two baselines, namely MobileNet and MobileNet plus SAM, by large margins, regardless of the metric. For instance, we surpass the standard MobileNet by 2% in terms of the accuracy rate. Here are some examples of cropped input images and associated pseudo-ground truth attention masks versus the attention masks predicted by SAM and SuPEr-SAM. In general, the ones predicted by SuPEr-SAM are significantly more correlated to the pseudo-ground truth attention masks than the ones predicted by SAM. We conclude that the illustrated examples definitely show that SuPEr-SAM helps the MobileNet classifier to focus on the right regions. Our contribution consists in introducing a pose estimator at training time, which provides a supervision signal to the spatial attention module incorporated in the classifier. Since the pose estimator is not required during inference, our pipeline adds a negligible margin to the overall computational cost, but provides important accuracy gains.